Hello everyone, this is Manisha Leemani here, and I'm presenting on Regression Network Module 6 Question 3 as part of Teach One Assignment course HAB 823 taught by Professor Wideman at George Mason University. Here is the question we are working on. We have a causal network showing the relationships between several variables, which includes severity of illness, provider's decision, do not treat, preference, treatment, and adverse outcomes. Each arrow in the diagram represents a possible cause and effect link. The direction tells us which variable influences the other. Our goal is to write an equation for each node based on its parents, then predict what would happen if treatment wasn't given. Before turning this visual map into equations, let's talk about why we even bother turning it into equations. So, a causal diagram shows us the structure, what's connected to what, but it doesn't tell us how strong those connections are. Equations usually let us put numbers to those arrows. We can measure the size and direction of each effect, figure out which ones are statistically significant, and then use the model to make predictions. The real power is in simulation running what if scenarios. For example, what if the patient doesn't receive treatment? How does that change their risk? That's exactly what we will do later with the counterfactual. Since most of our variables are binary, for example, treatment given or not, or if there is any adverse outcome or not, let's have a look on basic regression form. The logit function is the natural log of the odds. The intercept alpha is the baseline starting point when predictors are 0, and each beta coefficient represents how much the log odds change for each 1 unit change in its predictors, holding others constant. If a beta is positive, the predictor increases the odds. If it's negative, it decreases them. Now that we know the equation format, let's look at the network we are applying to it. Here are the equations for each node in network. Severity of illness has no parents, so it's just an intercept model. If we talk about do not treat preference, it depends only on severity and that effect is significant. Provider decision also has no parents, we just observe it in the data. Treatment depends significantly on severity, provider decision, and do not treat preference. Lastly, the adverse outcome, which depends on all four: severity, treatment, do not treat preference, and provider decision, but only severity and treatment have statistically significant effects. Moving towards the counterfactual no treatment situation. Counterfactual means we change a variable in the model to see how predictions change. This equation is the same as the adverse outcome model from the question, but with treatment set to 0. In the structural form, we still include E, which is error term representing a random component, but for prediction we use the expected value, which is 0. That gives us the simplified predictive form. To actually solve, set t equals to 0, insert model coefficients and a patient's value for severity, do not treat preference, and provider decision. Then convert the result to a probability using the exped function. Once you get the probability without treatment, compare that to the with treatment probability in order to estimate the treatment effect. Let me give you an example just for illustration, not part of the question. Let's say we have a higher severity patient S equals to 2 with no do not treat preference and a provider in favor of treatment. If we set treatment to 0, our model might predict around a 42% risk of an adverse outcome. Then run the model with treatment included, risk might drop to about 29%. That's a reduction of roughly 13.7 percentage points, which means treatment would lower this patient's risk by about 1 in every 8 cases. To conclude, counterfactual analysis gives us the ability to ask what if scenario questions and answer it with evidence. Simulating no treatment outcomes shows the measurable impact of interventions. This isn't just math, it's about turning models into tools that help make better decisions. And remember, the best decisions in healthcare aren't just based on what we know, but on what we can predict. Thank you.